So root mean squared normalization, or abbreviated to RMSNorm, is the process of taking in a list of numbers which tend to represent a vector. So that means a list of numbers like this, where you have number 1, and then number 2, and so on. And what you want to do is you want to set these numbers in a way that overall the numbers don't get too big so that you can't work with them, because there is a limit to how big of a number a computer can represent. So if the number surpasses that limit, then we get positive infinity, and that's not something we can compute with. Or alternatively, these numbers can get so small that the computer can only represent them as 0. So it can either go to 0 or positive infinity, neither of which are favorable circumstances, if we apply an operation often enough. So what has to happen is that these numbers have to be normalized or put back into an acceptable range for us to be able to work with them. In terms of a vector, what that means is that we may have a very large vector or a very small vector. We want to get them all to be of equal size. All the input vectors coming in over here to go into our RMS normalization and end up over here of the same length. Now, the way this happens is you have all of these numbers and you apply an operation called RMS to them. RMS looks like this. You have the first number of a vector, you square that, and then you add that to the second number of the vector, then you square that, and you go on. And then you divide this by the number of numbers you had in the vector, which is generally represented by the letter d. And finally, you take the square root of that. So you square the numbers first, then you take their average, and finally you square root them. This is RMS. And what this simplifies to, so in practice what this means is, you may remember that in 2 dimensions, the way you get the length of a vector is you break it down into one component, so one number, you break it down into another number, then you use Pythagoras' theorem, which is a squared plus b squared, square rooted equals c. And that's what we're applying here. If we simplify this, we get 1 over root d multiplied by v1 squared plus v2 squared. And that would be our case for 2 dimensions. These vectors aren't necessarily 2-dimensional. You could have multiple dimensions, but the same still stands. What we're doing is we're taking the length of a vector and we're multiplying it by some number. This number here is just determined experimentally. And since we have the length of the vector and the length is very large, then what we can do is we can take the vector and divide it by its length, which is represented like that. If we divide by a very large number, we get a smaller vector. If we divide by a very small number, we get a larger vector. This way, if we divide all the vectors by their length, which we determine using RMS, then we can get them all to the same size back into a range we can use to perform computations with.